So please, stage is yours.
Thank you very much. Maybe as a short round of introduction. So my name is Daniel Simon. I'm with the QA business unit as customer services, and with me I have Andreas. He will also introduce himself in a second. So we are the Axivion part. Actually, I like that logo up there in the upper right corner. So it's we are the color is called midnight. So it's that purple thing over there. So what we're going to do today is to introduce a little bit into static code analysis and how you can bully a static analysis tool. So you have no little. Meaning, of course, in practice you should probably not do it. But if you intend to, or if you plan to use a static analysis tool, we show you around what is making life difficult for maybe the static tooling, but also for you, and show you also how to work around the bullies a little bit. So maybe Andreas, starting with you.
Mm-hmm. Yeah, thank you. Yeah, you see, we will try to share a little bit our fair share of things, and take everything you hear with a little grain of salt. Yeah, maybe you had now lunch, you are digesting. Yeah, and we hope it will be a little bit entertaining for you. Yeah, do not take everything too seriously that we say here. You see it already from the title. Yeah, how not to build a static analysis tool. So one of the things that we would like to tell you is how you can live together peacefully with your static analysis tool, and maybe also make your tool happy, because also tools require some love. Yeah, so this is very important. Yeah, right now with artificial intelligence, who knows? Yeah, then maybe they have also feelings. Good. Just to have a small recap, what is static analysis? I think most of you will already know. Just to have a small recap, we analyze source code without actually executing the source code. Yes, we are doing not testing. We are actually just look at the source code and do analysis on them. And a static analysis tool outputs an alarm that points you to a code flaw or maybe to a bug. Yeah, so this is what we are actually doing. And this might look like this. Sorry, it's a little bit small. Hopefully you can see it in the back here. What you can see here is a screenshot from our Visual Studio Code plugin, where you can see, for example, these small markers here on the side, like with autocorrection within Word. Here you see here certain kinds of markers. And you see down here a list of things that could go wrong. For example, here's pointer maybe null at dereference, possible division by 0, and access into array might be out of bounds, as a few examples. You see this here, the tool actually tells you that. And we would like to start with a small intimate discussion with your static analysis tool. Yeah? Let's call this guy Bob. Yeah? So Bob has a list of his findings, and now he looks at them, and he has some kind of arguments and some kind of comments about what the static analysis tool reports to him.
I'm doing the opening for the first kind of check. But before I start, just a question to you. Who of you is using a static analysis tool in whatever sense already? Oh, that's good. So I don't have to explain the details. But static code analysis in the broadest sense starts already if you just use your search function of your code editor. So you don't execute anything when you look for a variable name, a function name in your search function. But that's already static code analysis, because the tool, the IDE, has to search through the static code without executing it. That would be the easiest thing. And now we start with the first category of checks. And I want to introduce one simple check where you have to think a little bit. So maybe let's start with, you all know how to code C++, right? Nodding. Good. So the first thing is now we have a macro, which is maybe not best practice to use macros anymore, but people do it, and your library headers will do it, so you have to be aware of it. Now the first question is, what does this macro do? So it's called a define square of x. And this is x times x, which is usually the square function. So name sounds reasonable. It's maybe a little bit short because there's accidental overwriting of such kinds of things, and then you get into trouble when you have several macros of the same name, and maybe you collide with something in the standard headers. Now the first question for you is, what is square 5? Anyone? 25. Okay. Next question is, what is square 2 plus 3? I heard different things. What is it? Oh, really good. So you've seen that example maybe before. But yeah, sometimes it takes a little bit longer to just get it because yeah, it's a pure textual replacement. So what happens in reality is 2 plus 3 times 2 plus 3 is 11. Okay, so what does it mean? In that case, the expectation, it's no longer, well, would you expect to be at 11 if it's called square? So that's why this is an issue usually when you mistake this. The solution is also quite easy now, and this is how you make up programming rules, because you stumble over this several times, and it really messes up things, because this is hard to debug. You will never see this in your debugger, in the printouts, and it's just, well, we put in a 5, and it comes, but it's 11, and then more macros. So the rule would be that we have a programming rule just like demanding the correct tracing. So on the lowest level, we just have to look at this defined square, and we see that with a little bit more braces, parentheses in that case, you can have a proper result. So even if you now just use it in this version, it will be 25 in both cases. Much less surprise for you as a programmer, much easier, or hopefully easier to debug. At the end, that's the easiest idea of a very small static code analysis. So we're looking at this square. You just need the context of the square and provide a programming rule. And the second part of this static analysis, what Andreas already showed, is we do not only analyze, that would be just half the way, but you also need to report things. And the report can then be, well, put your parentheses around it, or in the search function, just show me what you just searched. Well, that's the easiest one. And now we're getting things are getting a little bit more involved, and that I leave to Andreas.
Yeah, not that much, I have to say. Well, if you maybe look at this wonderful function, except that it has a not so nice name, could you maybe spot something here? A problem. You can just shout it out if you like. Yeah, very good. Yeah, so there's already the test case, so to speak. Yeah, the problem y equal to 1. Then we have a problem here, and this is also what a tool might report: a possible division by 0 on this in this program here. And Bob is grateful to the tool. Yeah, he says, "You're right, tool. Yeah, that's very good. I will fix that. Thank you. Very good." But maybe there are also things like this here. We have here another, a little bit more elaborate piece of code. And here the static analysis tool says, well, pointer may be null at dereference. But somehow, well, there is a check here. So you just say null pointer here. It's a C example. Sorry for that. Yeah, it's a little bit older example. Maybe Bob says, don't you see that I checked for null before that tool? What do you want to tell me here? So this might be something that you all know, which is called a false positive. Yeah, something where the tool reports something, but there is actually maybe no problem there. Yeah, we do not know because there's a little bit of stuff that we've left out. And sometimes it might also be, it depends on the tool, and what the tool does. Maybe the tool takes some time, to compute things, So, well, a lot of things. But maybe now the tool also thinks something. Maybe thinks, what's going on here in this code? Why do you demand so strange things from me? Yeah. So, do you try to make my life difficult? And maybe both think something, what a bully, So maybe the programmer, Bob, thinks that, and maybe the tool thinks that. And could we maybe do something that they are a little bit nicer to each other? So this is what we try to do here. And for that, we have to understand each other. This is very important that we know about each other. And so we will talk a little bit about static analysis tools and some of their properties. So we have already seen a few alarm categories, and we know there are a lot of things that you can check with a static analysis tool. Use of curly braces, or we have seen the macro example that we had before. Things like naming conventions of variables is also very important, that you have a consistent naming scheme is very often checked. Then calling functions marked as obsolete, for example, do not call still copy, because this might be a bad idea. Division by 0, and things that have to do with memory allocation. You have a memory allocation without a proper deallocation. This is also something which is a bad thing. The thing is, they seem to look a little bit, they have a lot of similarities, but they are quite difficult it's a little bit, how to say, we have to categorize them because some of these problems can be done purely syntactical. So the tool only has to look at the syntax of your program to actually tell you whether there is something wrong. Then we have some kind of gray area, and here we have things that are semantical properties, so things that have to do with the things your program computes, yeah, or the running time, and etc. And these things tend to be undecidable. We will talk about this in a second, yeah. And there are things like gray areas, like this calling function marked as obsolete. Here it depends, will you also consider indirect calls? Then it can also be undecidable, yeah. And but if you only look at direct calls, then this is, for example, something that can be decided, yeah. So a few runtime error categories, maybe to refresh your memory. Most of them I think you already know. We have here a small C program with a lot of unsigned variables. One of them we have already seen, possible null dereference, this star P element here. We see this, there is an initialization of this P, but we do not know what get actually returns. So it could be that it's still this null value here. So it could be that this is a possible null dereference. And we have already seen here, we are dividing by star P minus 1. So we could also have here this possible division by 0. And there are other things like wraparounds. So a wraparound with unsigned in C is not undefined behavior, but sometimes it's unexpected. Yeah? So sometimes you also want to know that there is a wraparound here so that you actually have a larger number, and then it's a computed modulo, for example, of 2 to the 32 in this case. And another category, which is quite interesting also for safety reasons, is to have something like buffer overflows. Yeah? If you look here, you have this is the classical example. Yeah? X is smaller or equal to 3. If you look at unsigned R3, 3 elements, yeah, this is a very frequent error. Yeah? You have actually, you access R of 3, and this is bad. Yeah? You should not do that here. Mm-hmm. Good, and now let's look a little bit at properties of these tools. How do they detect these things, and what kind of categories are there? We can do a rough categorization of static analysis tools, and I have to say already a lot of tools offer all these 3 categories that we will see here now, yeah, and you can configure them in a certain way. But the first part, I think we all know things like linters, yeah, so simple tools that do syntactical checks, no deep semantic analysis, but are tremendously useful, yeah. They have cool features and look at certain programming patterns that you should avoid and are normally quite fast. Then we have tools, we call them now bug detectors. They go already a little bit further. Yeah? They look at runtime errors, at the semantical stuff, division by zeros, yeah, error out of bounds. But their approach is they do not try to find all possible problems of such an error category. They try to find things that are most probably real, true findings. Yeah? There might be really something wrong there. Yeah? This is what their target and objective is. And then there's another category, the so-called, let's call them conservative tools. Yeah? These are tools that also detect runtime errors, but here normally they try to report all possible problems that are in such an error category. So they also employ normally a lot of kind of sophisticated analysis techniques, like a buzzword here would be abstract interpretation, etc. Yeah? So there are a lot of techniques that you can employ there, and they have to have a kind of mathematical solid model behind them. Yeah. Good. And how can we distinguish them? So we will a little bit stress on these conservative tools, yeah? Because these are the most, the most fun one, yeah? What do conservative tools try to be? They try to be sound, yeah? This is a very important and a little bit overloaded term, yeah? We will define soundness here. If the tool does not report an alarm at a code location, for example, there's a division and it does not report a division by 0, then if the tool is sound, no error can occur at this location in any program execution. Yeah? This is like a guarantee. If the tool says it's sound, yeah, then there is no such error. So if there is a possible problem, you know there will be an error there at this location. Yeah? There will be an alarm of the tool. And this means the tool has no false negatives, so you cannot miss an actual problem here. Yeah? This is the soundness direction. Of course, there can still be bugs in the analysis tool. You can configure your tool wrong. There are a lot of things that still can go wrong, but this is the objective of a sound tool. And you can turn it around. Yeah? You can have the other way around, which normally is called completeness. And what does this say? Error cannot occur at a code location in any program execution. Then the tool also doesn't report anything. You see, this is just a dual. Yeah? It's just the other way around. So there's no alert or no alarm if there is no problem. Yeah? And so here you have no false positives, yeah? Which is, of course, something everybody likes. Yeah? But, of course, now maybe you think, well, there's soundness, completeness. Couldn't we just combine these two? This would be the greatest tool on earth, yeah? We have no false negative, we have no false positives. Wouldn't this be great? It's here in this cloud, yeah? It's the cloud here. It's a beautiful paradise-like situation if you could have such a tool. Unfortunately, Mr. Turing, he showed us that there is a little bit of a problem because C and C++ are very powerful languages. You can do a lot of great stuff in them. And this is also a problem because you can prove mathematically that since these are so-called Turing-complete languages, at least idealized Turing-complete, no tool that always terminates can be sound and complete at the same time. Yeah? You cannot have such a tool, unfortunately, if you want a tool run automatically and always terminating. Yeah? And this is something I think you like to have. Yeah? So this is not okay. So no idea here.
And the easy way to know false positives is just turn off any check. And you don't get anything. The other way around is just report everything.
You can have beautiful tools that are sound or complete, but they are not that useful. Yeah? And you see here now, we need a sweet spot. We need to know what actually do we want in our project and in which direction would we like to err. Yeah? This is exactly the point. Yeah? We have either to over or under approximate alarms. This is possible. Yeah, we can do that. And conservative tools normally tend to only report false positives. Yeah? So you can have a lot of errors and normally or alarms, and you have to look at them and see, is this a real alarm? Yeah? So there's the human involved again. Yeah? And normally, for example, with the Axivion suite, you can control whether you want an analysis more on the sound side or on the complete side. Yeah? So normally tools offer things to actually control that. It also a little bit depends on your approach and if you are safety related, etc. Yeah, so this is something.
Maybe to add to that has some impact on the usefulness of tools and depending on your role. So we have quite some customers who say, well, I'm safety manager here, so I don't care about false positives because that's something the developers have to review and prove me that it's not going wrong. On the other side, if you have a lot of false positives, that's not very useful for the developer because they have to review all that stuff. So there's contradicting targets also here, and then this moving it from one extreme to the other, that's the art of choosing the right level.
That's true. And now, of course, since we say how to bully or not to bully, yeah, we see here what conservative tools do. So we have normally, hopefully, a lot of locations without any alarm, yeah, but you have also locations with an alarm where the tool says something, and embedded in them are the real alarms, so the real problems, yeah, that are there. And of course, our mission now for the rest of the talk is, with a blinking eye, how can we actually do this? Increase the false alarms, yeah? But you can also, of course, do the other slide in the other direction, and maybe you can use some of these tips here also to reduce the false positives of your static analysis tool. Should you have some, yeah? Should you have any? But normally you have if you have a conservative tool, as we've seen before. You cannot avoid it. So just a short interrupt here. So can't we just brute force look at all the executions of the program? Let's test everything. Yeah. In some cases, this is possible, yeah, to exhaustively look through the whole program space. But for example, in this small function here, you could easily compute. You have two unsigned variables. If they have 32 bits, then you have 10 to the 19th, a little bit more possible input combinations that you should check. Then you are a few thousand years. Normally, with today's computers, you have to check those through, yeah, all this. So normally the tools don't do that. Only in very restricted areas they can apply such techniques, so this is not feasible. What the tools do is they apply certain techniques, and I just want to show you one of these techniques that static analysis tools use, which is abstraction. Yeah, abstraction, as always, a very overloaded term. What this means here is we over-approximate program states. We do not look at the single program configuration or program state. We try to sum them up into larger abstract states. So instead of, for example, tracking single value combinations of x and y here, let's just track ranges of values at certain program locations. Yeah? So for example, here we have a few program locations, x and y, these dots here, and you see them here summed up. But this is this costs a lot of memory, yeah, to save. We can just say, well, let's just say x is in the area between 1 and 20, and y is in the area between 0 and 10. Yeah? Just have this rectangle here. And we see here there are a lot of dots that are actually not in this set, yeah? But we just say, well, just over-approximate it. Yeah? We know that this is now the range of these two variables. Yeah?
At that point, that also reminds me always a little bit about when you do testing. So this is like you do an interval analysis of your test inputs, and then you do pretty much the same. Now this is just done without executing the code, and thereby limiting the effort and the amount of resources you have to put into getting a result.
Mm-hmm. And now let's go back to the example before. So Bob has seen, oh yeah, there is a division by 0. That's true tool. Yeah, let's fix it. Maybe it's a very simple fix. He just says greater than 1. Yeah, and now let's see what the tool does. Yeah, with this very simple technique that we learned before. Yeah, we have here again our small function, and normally the analysis works on something which is called a control flow graph, just a graphical representation of your code. Yeah, flow graphs. I think it's quite. One knows, has seen them before. So we see here, for example, this node. This is actually a screenshot from one of our tools, yeah, that also can display control flow graphs. We see over here we have this condition y greater than 1. We have a then and an else branch, and here these two returns. So this is just this program in a certain graphical representation. And now, how does the analysis work? Very short. It starts here. We only look now at y because x is not important here for the division. Yeah, we look only at the values of y. We do not know what value they are at the beginning. Maybe we know they are between 0 and 2 to the 32 minus 1. And then we have this then and else branch. And here now we know, well, y is greater than 1. We can restrict the range. Yeah, we can say it's from 2 to the maximum value, and here it's between 0 and 1. And then, of course, if we compute now this y minus 1 symbolically, yeah, in this with this range, we know the range is between 1 and this maximum value minus 1, so 2 to the 32 minus 2. And of course, there's no 0 in there. Great, yeah? This means no alarm. The tool can know that there can be no problem here. Yeah? There can be no division by 0 problem. There can be other problems, but this is not a problem that can happen here. Great, very nice. So this is good, but we want to bully the tool. Yeah? So what can we do? Well, we can just use very complex computations now instead of this y greater than 1, relating multiple variables. Yeah? For example, we write something that looks not that bad, yeah? X times x plus y. And we check this here, is it greater than 0, and we just divide by it over here. So it's a nonlinear expression, x times x, yeah? And we have duplicated this computation here. Maybe this is already something you think, this is a little bit strange code, yeah? Maybe I would have written it a little bit differently. And then that's very good, yeah, if you think that. If not, let's just try it out. If we only use this range abstraction now, these kind of ranges, then you can actually think about what is now happening here. So we know x and y are again unknowns, and now here the analysis knows about this expression here, but you can actually compute. This does not help anything. You cannot restrict the values of x and y here, so they will be the same. Yeah? So you cannot actually use this condition here, which you actually need. And then, if you know x and y is still in the range between 0 and the maximal value, then you know here it could also be that x is 0, for example, and y is 0. So you have to report something here if you do not use any other techniques. Yeah? If you only use this range analysis. And this is bad. Now you have a false alarm. Yeah? This is really a false alarm here. I have to say, take it with a grain of salt, yeah, of course. I do not want to say that, for example, we do not detect these false positives, yeah. We have other techniques that we use, more powerful numerical and control flow abstractions and techniques. And we are also here, you saw these two expressions that come 2 times. We actually track things like that, yeah. And also, of course, this is something that a lot of tools do, but this is just for you to see. This is something, this kind of patterns can be extended. And I would say, I think I can say that every tool regarding every tool out there, you can find such a bully in a very similar way, because somewhere the tool has to abstract things. And if you know where it abstracts, then you can construct such a real bully. Yeah? And also the thing is, you can get rid of this bully, but it might cost you. Yeah? It might cost you time and memory, yeah? to actually have more sophisticated techniques applied here. So what can you do? We want not only to bully, we want not to bully. Yeah? We want also to have a mediator here. Yeah? We want to have something that helps. And here, this is a very primitive help. You can actually use a temporary variable that stores this x times x plus y expression. Yeah? And this is not only nice now, because if you look at the code now, you have here this diff is greater than 0, and you divide by diff. And here now the analysis can, of course, again infer that this is between 1 and 2 to the 32 minus 1. Yeah? And this is great, so we will not have a fault here. But it's not only good for the analysis for the tool, it's also good for you, because you do not have this double computation of x times x plus y again. Because if you see, well, I have to have a 2 here, normally in your old code, you have to add this in 2 different locations. Yeah? So you have a little bit of a code clone here. And if you have it in one place, you only have to evaluate it once, yeah? And you can actually have one place where you have to change it if the code has to change, yeah? If the computation has to change. So it's not only for the tool a nice thing, it's also cleaner code. Yeah? It's also nice to have this here.
The idea here is that the tools try to help you to prove that the code works as it was intended. So that's a little bit of, we are not here to show you that it's wrong. It's just also supporting you to show someone else that it works by not having the false alarms.
Mm-hmm. Good, yeah, there's another example, you can extend them, yeah, for example, maybe you could ask, could the tool not do this automatically, yeah, say, well, move this around. Of course, you can, for example, have function calls in there that might have side effects, so you have to be a little bit careful here, but yeah, you can extend this bully as far. And maybe if you use a static analysis tool like the Axivion suite, you can see that this is a pattern that you might, yeah, maybe you remember this then if you have a similar finding, yeah. I would like to add one more bully from my side, or two, one, let's see in the time, maybe one, let's see. So the one, you have seen this example from before, where we have actually a global pointer here, so we have a global variable. This is also, of course, something you should not do, but this is used in this code. And you have here, for example, if global pointer is not equal to 0, and then the dereferencing. So this normally is no problem for a static analysis tool. This is great code, and you would not have a fault here. But what you could do to anger the tool a little bit, yeah, just move all the stuff that is done here in this if branch here. Yeah? Work 1, work 2, maybe a lot of other stuff that is done here. Why is this a problem? Well, the tool has now to prove, yeah, if it's a conservative tool, it has to prove that global pointer is never written or accessed here within these calls. Yeah? So you make its life a little bit more cumbersome, yeah, in this place. And actually, again, this is also code that maybe your coworker has a little bit more trouble understanding. Maybe if you want that, then you can do that, yeah, but you should not want that, of course. So here also, this is also good software engineering to have to check actually quite near the actual use, yeah, if this is still the same semantics. Yeah. And then just one short sentence about one more bully, which is a little bit more general. Be creative with calls and control flow. It's always good, yeah, to have a function that has a lot of multiple tasks, that uses a lot of variables and control flow branches, and is called by lots of different other functions and classes. In German, we say eierlegende Wollmilchsau. Yeah, you have one function that does almost everything in there, and this is nice, and you just add functionality to that. So why is this also bad for the static analysis tool? Well, for example, here you see a call graph. It's also a screenshot from the Axivion suite. You see here is a function which is called log and update. You see an and in a function name is already a good sign if this is in there. So it writes log messages, and it also updates some kind of program state. It's called by a lot of other things. These blue edges are just call edges. Yeah, it's called by a lot of stuff. And why is this now bad? The problem is normally the bully, of course, on the software engineering side violates the single responsibility principle, but also normally an analysis tries to make a summary, some kind of a summary information for a function. And if there is some kind of imprecision in this function summary, then this propagates to all the callers. Yeah? So if you do not know the range of this variable, it might propagate to all the things that calls it. Yeah? And so you have imprecision everywhere. This is very, so you can bully your static analysis tool. What can you do about it? Yeah? You can actually verify and maintain a software architecture, because in a software architecture, you would see you have this function which is also used by all the other stuff. Yeah? And if you verify that, then you see this already in your architecture. There's something missing here. There's something strange going on. This looks a little bit strange in your architecture. Yeah? And also, the tool can even help you in another way. You can also compute metrics like number of incoming calls. Is a certain metric which this log and update would have a very large number. And this is reported to you, yeah, with a very simple analysis. And so you can also see there is a bully, yeah, and you can actually use the tool itself to get rid of the bully. Yeah? And again, this would also mean that the software quality is improved. Okay, then I think a last bully.
So that was all the nitty-gritty low-level stuff. And you see that's just a very small program. So in practice, that's hundreds of thousands of functions and control flow statements, things that go around. That makes this static analysis tool pretty busy. Now I'm trying to abstract a little bit from that low-level bullies a little bit to more the higher level. Andreas was already talking about software architecture. So now we're thinking in the black boxes are components, and the arrows in between are some messages passing, function call, something. It's intentionally very abstract. So we could start with message passing between two components. So we have an A and a B, and we call something that sends data. Well, this is now the most simple representation. We have just the two components. Now this is very static, of course. And if you want to reuse that code, it's probably difficult. And sometimes you come to the idea we can now make this a little bit more abstract. So we may have some similar use cases where you have now an A talks to B and C talks to D, which is still very static. So you know that this message sending just can happen between the two, but A will never send to D and C never to B, and not the other way around. So this is very simple. We could increase the number of communications between those components, maybe by just summarizing again, like in this log and update function. Now we have a send, and the parameter was sending to. We just put this as a runtime decision. So instead of statically calling, we go for runtime, which makes life maybe easier because you just have one send function, but also for the static analysis, it's more difficult. So you could use array indices. So if it's not only two components on each side, but a whole list of them, then the more you make it dynamic, the more interesting it will be to decide what really happens at runtime. So there's always a choice between, say, the complexity in the architecture and the complexity in the analysis. To make things even worse, we could simply introduce a mediator here. Again, we don't call directly through a dispatching function, but we call to some message queue that saves data in the database, and 5 days later it sends back and the messages get received on the other side. So the more dynamic, the more at runtime things happen, the more difficult it will be for our static analysis tools to show you if it's right or wrong. And that's the big challenge here, not to, well, the good thing about these abstractions is you are more flexible in combining software components. The bad thing is you don't know what you combine anymore, which is more difficult to analyze. Message here is be as flexible as necessary, but don't overdo it. Sometimes I've seen software projects, they are already at the message queuing level, but they only have two components. So that's an A, that's an B, and nothing in between. So keep it as simple as possible, which gives the static tools a chance to help you proving that it really works. Oh yeah, and finally, we could even go to subscribe and publish, so services dynamically, plug and play at runtime. So have this not only in one language, but use XML, JSON, databases, just message publishing, subscription patterns. And then at some point in time, you will lose any information of what's going on at runtime. And statically, we can just say, yeah, there is something. We can still revert back to checking those communications patterns, but there it stops, and the rest is up to other sources of information. So that is the 4 bullies we wanted to present here. maybe let's reflect a little bit of when to use what class of tools. So Andreas started with the very small things like linters. When would we use that? Ideally on I save the file and then you can check. So that's something that you can repeatedly use. It's easy to integrate, short turnaround. It's really that most of the linters you can run nowadays on save my file and do the check, report back the issues the linter finds and fix it. It's easy to integrate. Downside is it has a very small scope. So the linter, if it only looks at one file, at one compilation unit, it can only tell you things about the compilation unit. If we start with bug detectors, that's more complex now. It's relatively short turnaround times, like minutes. Maybe the nightly build can do that in a few seconds. It's still doable with a feedback loop that's useful in daily use, permanent use. Again, can be integrated in the development environment. Still, the scope is wider than just the linters, a little bit wider, but not complete. Now, let's come back to these conservative tools. Everything that Andreas showed us is doing a lot of computations. It propagates value from A to B, it tracks function calls, a lot of complicated stuff, complex stuff that needs resources, and has the largest scope. So those tools will find a lot of things that you cannot see on just one compilation unit, just by on save. You need more information because you need the whole system, not only just one compilation unit. Maybe you need even to see different variations of your system when you have if-defs in your code that behave differently on different targets, and there need to be maybe even more than just one analysis. Interesting thing is that most of the conservative tools simply are really complementary to the linters because they just don't care about the nitty-gritty stuff. It's all they're doing just the fancy things. Turnaround times are really depending on your code. So they have false positives. You need to check that. And the turnaround times is, let's say, I've seen projects where such a tool runs in 10 minutes or across 1.5 million lines of code. And I say, yeah, code is good because, of course, it's also good impression from us. But then there's also 20,000 lines of code where the static analysis takes hours, which is, again, feedback on if the tool takes hours to review the code, would you be faster, or what's the alternative to that? So the ideal set is you use all of the different tools for the respective purposes in different points in time. So you could just use a linter that is consistently configured with the bug detectors and conservative tools. And then after doing your commit and push, something happens on your pull request. That could be the bug detector. And in the nightly build, when everything is merged back into your overall system, that would be a good place to use the conservative tools. Downside is you have 3 answers for the similar questions at different points in time. And so the sooner you find something, the linter will be easy to fix because it just happened. The bug detector might be catching things in your reviews. Conservative tools are really slow at the take, and you need hours for running them. So it might be the next day when you find things, and then you need to go back to your linter bug detector. But that's currently, I think, the best approach. Use all of them at the right point in time, and take their different advantages and try to keep those 3 things in sync so that they don't report inconsistent messages. Maybe to close that, if you think about more bureaus, so if you have somebody who wants to give you a static analysis tool and you want to send them away, just ask them for, what about dynamic constructs, like remote procedure calls on a different machine? What can your tool do there? So it's probably not too much. So that's a challenge. If you use that stuff, you need to model that information that is missing from the static perspective in a reasonable way for the analysis. So the real question is, can we model that behavior in a way that the analysis can pick up the information and then use it for the local analysis?
And of course we can. So
yeah, but that's the question you have to ask. The second point is, there's this ZOOP component, so software of unknown origin or of unknown pedigree, third-party components without source code. So you just see the header files, and you can't look through what's happening inside. That's a big issue. So at least you need, as Andreas said already, with these unknown get functions, you need to model that summary of the function. So if you use a third-party JPEG library and you issue function calls, you should try to get an idea of what's happening there by maybe reading the manual or trying to get the source code. But if you see that kind of function calls to third party, it's always bad for the analysis because the analysis needs to just fall back maybe to, instead of values, to types, so you have the maximum value range. That's difficult. Another interesting thing is if you ship a library for your customers and they just use the libraries, how do you assess that? Because you don't know the application. Ideally, you probably would say, oh, I have a report on my checks for the library, but dear customer, do also the same when you use the library code with the application. Sometimes things just, it's right here, it's right there, but if you combine it, it's broken. An interesting thing is using test and application code. So you can use test code also to check things, particularly if you have libraries with static analysis. Mixing test and application code can be a challenge. And what's always good is, well, we need time, everyone needs time to implement fancy constructs. And if you look at the speed, how C++ is currently evolving, always try to use those super fancy things that looks like the developers bumped their head on the keyboard instead of C++, but it compiles. So things like spaceship operators was the newest one. What's the thing that they did not yet implement? The modules? Modules. So if you try that, probably you won't find anyone who knows how to analyze it because it's even not compilable in the most compilers. But that's a challenge, and most of the time, the more advanced stuff you use, the more difficulties you will have to find a tool that accepts the same code for analysis. So, final words. All the different tool categories have their pros and cons, from speed to cost and sense of resources, how you integrate that into your CI DevOps, into your daily development workflows. A good idea is if the tool has difficulties, you probably also will have difficulties with the same code, so make it simple. Sometimes it's like the refactorings Andreas showed, it's easier even for the tool and for you and for your colleagues. Follow these good software engineering principles. Don't do 10 different things in one function just that confuses tools and your colleagues. Architecture checking and monitoring the metrics of components is also something. It's a recommendation. So if things get too big, just refactor that. Yeah, and know what the tools can do and what they can't do. That's what we try to give you a little bit of insight today. That's it. Final words, Andreas?
Just if you like to have a nice bedtime read, yeah, there are also nice books. Not from us, so it's just really a neutral one. And of course, the website for quality assurance is a good way to start with this topic. Yeah, I'll continue. Thank you.
Hey. Thank you.